For this next one, it says, given that x squared plus y squared equals 3, please find y double prime in terms of y. And that means the second derivative, right? So I like this notation. This is the moment where if you want to try this, go ahead and pause me and try it your way with y primes instead of dy dx's. And when you're using those y primes, you don't write anything when you do the derivative of x, because remember that dx is equal to 1. Then when you're done pausing, you come back and you can check my answer here, okay? So I want to say, and this is a perfect moment for me to say it, that the notation for taking the second derivative actually has a place in my heart, very special place in my heart. If I take the first derivative, d dx of y, I should get dy dx, and I already showed you how I get that. But if I take the derivative again, d dx of dy dx, it really works like this. The d's get squared because there's a derivative d and a derivative d up here, and I square those. The dx's get squared together, so I see a dx squared. That's where that notation comes from. I'd already introduced to you that this thing means the second derivative, but you had already forgotten, and that's okay because it looks weird, right? But now that you've seen me do implicit notation and you've seen the Leibniz notation, you could see why I'm going for it. By the way, those of you that love this y prime business, this is Lagrange. And the Lagrange notation is very popular because it's the most lazy version of it. But we will mention that Lagrange and Leibniz notations. Leibniz came first, and he was actually a master of notation and is one of the fundamental discoverers of calculus that nobody can dispute over and over and over again because he perfected notation. All right, the notation that Newton created is still hardly used at all except by physicists. So the fact that Newton and Lagrange were both Newton and Leibniz were both contemporary, they were colleagues from across the countries, one of them in two different countries. It's interesting, but Leibniz's notation has endured because of its usefulness and the fact that it logistically, it makes sense, okay? So when I go ahead and work out this problem, then I clearly am going to need a little extra space, okay? So here I'm going to give myself some room, and I'm going to attempt to work this problem out then with my Leibniz notation. So finding the derivative of x squared plus y squared equals 3, I will say then that I have a 2x dx dx. I have a 2y dy dx. You see how it just feels natural? And then the derivative of 3 is 0. I cross that out. Again, it feels really natural. I'm going to minus 2x from both sides, and I'm going to say that I have a 2y dy dx, and that equals a negative 2x. I want to divide by that 2y. I want to divide by that 2y. I don't write that down just in terms of saving space and time. Dy dx equals a negative 2x over a 2y, and I can reduce that to a negative x over y. Wow, that was really easy. Okay, so that's my first derivative, negative x over y. And for those of you that are doing it with the y prime notation, you can then say that you have y prime equaling negative x over y. And Mr. Taylor picked this example on purpose because he wants you to learn how to do the quotient rule with two functions that don't use the same variable. So again, this might be one that you want to memorize, but obviously you will need to be able to come up with an answer to this just basically all the time. And I myself, I'm not even going to bother with a negative version of it. I'm going to throw my whole answer in and then make it negative when I'm done at the end. So what I want to do right now is just finding the derivative d dx of x over y, because negatives mess me up and I don't need them in my life, all right? So if I take the derivative of x, I will get a 1 dx dx, which I can cross out. And when I take the derivative of y, I get 1 dy dx. And so my derivative of these two things, remember how the quotient rule works, something times something minus something times something over something being squared. And what is in the bottom is supposed to be the original denominator, and that is squared. And it also goes up here on top. And so if I've done y, then I need to multiply it by that, and then I will need to multiply this times this. So this will be where I put my dy dx, and this will be where I put my x, and this will be where I put my 1. And I believe I can simplify that and make it look just a little bit neater. And I will do so when I plug it in right here. Ready? My dy dx is really a d squared y over dx squared. That's my second derivative. I'm going from here to here. Say that I have the negative version of y times 1 is y, and dy dx times x is really x dy dx. And I'm throwing that all over, ready, y being squared. And can you leave this answer like this? Indeed, you can if you want to. All right? Now, having said that, though, I do recall from my days with my calculus teacher where she said that if you can simplify anything out, sometimes miracles happen and it makes it look nicer, okay? So I would say that if we know that dy dx is negative x over y, it is probably true that we can make this look a little bit neater, all right? So how would that look then? Well, dy dx is negative x over y, so I want to throw that in. And I will say now that I have a negative y plus, well, I don't want to distribute the negative while I'm also going to plug in something that is negative. That messes me up. X times, this is negative x over y, and then I want to have my y squared all on bottom, and I will work this out to be a negative y, and here this is x squared and it's going to be positive, and then I have to make it negative anyway, so this will be a negative x squared over y, and the whole thing is over my y squared. And do you remember how to clear a fraction of nested fractions? You might not, so I'm going to go slow. And if you do know how to do it, then why don't you pause and try it, and you'll get to the same answer as I do, but potentially with fewer steps. So if I have a denominator of y, then what I want to do is I want to multiply everything by y. I want to multiply this whole expression here by y, and I want to multiply that whole expression there by y. And then what happens when I do that is I'm distributing a y here and I'm distributing a y here. So what I'll have is a negative y squared and minus an x squared y over y, and this whole thing will be over y cubed. And then when I am going to keep going to the next step, I'll have a negative y squared minus, now these y's cancel out and I get minus an x squared, and this is all over y cubed. And that looks actually pretty good in my opinion. I like it. Now, here's the question. Does your answer match my answer? It might not. And here's why. Because the way that you clear your fractions can cause you to end up having things that look slightly differently. You know what I mean? So what I want to say is that there is a chance that your answer, how do I say this? AP College Board may have messed around with your mind. If you look at the multiple choice answers, you may find that they have substituted either for y squared or for x squared. In this case, I would say they would substitute for x squared. And you're like, well, what do you mean? And why would they do that? Well, let's take a look again at the original problem because it's way up there. It says that x squared plus y squared equals 3. And this one actually, like I said, could have been solved for y. It would involve some square roots. It would involve taking, the power rule on a square root. Then you want to have a denominator that has a square root. It's pretty ugly, all right? It's not my favorite one to take the derivative of. But specifically because you can take this x squared plus y squared equals 3 and then minus y squareds from both sides, that's actually a pretty simple process. X squared can be defined as being 3 minus y squared. So in our problem then, they could give you an answer that looks like this: negative y squared minus 3 minus y squared all over y cubed. All right, and why would they do that? Well, it looks to me like what we end up getting is going to be negative y squared minus 3 plus y squared, and this is all over y cubed. They did this because the y squareds cancel out, and my answer will be negative 3 over y cubed. So please forgive me, but I did want to go and double check my answer and make sure that I'm 100% certain that it is correct, and it is. And when I was coming back and looking at these notes, I'm writing down that, hey, what I'm doing here is a cute substitution trick, and the reason that I'm doing it is that the second derivative only has one variable in it now. So for number 5, then, given cotangent of y equals x minus y, find dy dx. And here he's actually saying that he's going to use the dy dx notation, but it's funny, when I look at his answer key, he's still using y primes. So it's up to you. And finally, on this last example, if you want to see one with y primes and decide that you like y primes, that's fine. The derivative of cotangent of y is negative cosecant squared y. And I always write down that I am finding a derivative, so here's where I write down the y prime. And then I'm going to take the derivative of x, and I'm going to get 1, and because I'm doing it your way, I'm not going to write down the dx, and then I'm minusing y. The derivative of a negative y is a negative 1, and it is a negative 1 dy dx, which I'm going to write your way is the y prime. Did you like that? I don't know. This is the moment where I get really super weirded out. I don't like that y prime being behind as a product of cosecant y squared without parentheses there. I explicitly put down the multiplication dot, but I really don't feel like that notation is clear until I put a parentheses there, okay? So that you know that the function cosecant is being squared with an input of y, and that's it. No other input. Y prime is not an input to my cosecant function. So in that case, then, I'm going to move it around. I'm going to say this is negative y prime cosecant squared y, cosecant squared y, minus 1 minus y prime. Now that it looks a little bit better for me, I'm going to add y prime to both sides, add y prime to both sides, and I will see then that I end up with a y prime. Here, I'm going to do this right here. I have a y prime minus y prime times cosecant squared y, and that equals 1. Now, these are not like terms. So right here, this is its own term, and this is a different term. Cosecant of y squared is like, imagine it as a constant. It's a multiplier for that y prime. That's the yellow. The pink, y prime's multiplier is a hidden invisible 1. So what I want to do is I want to factor that out. So I'm going to say then that what I have is this notion that I am factoring out those y primes, and I'm going to throw them in front. And what I have left is a 1. There's my hidden invisible 1 right here. And I'll write it in red for you. There's a 1. And then there is the rest of this, which is cosecant squared y. And then on the other side of that equal sign, I still have a 1. And so when I divide by this and I divide by this, again for time and space, I'm just going to write down that y prime equals 1 over, and here's my whole coefficient of y prime. It's 1 minus cosecant squared y. No cute substitutions allowed here unless you were to recognize that there is actually an identity, okay? And this identity, you may or may not be familiar with it, but if it is a multiple choice problem, they will say that 1 minus cosecant y, cosecant squared y, you might recognize that as being the same thing as, well, if you factor out a -1, then this is cosecant squared y minus 1. And by the way, now that I say that, do you remember that there is an identity, and that identity is called cotangent squared y. So this is ready, 1 over -1 times cotangent squared y. And that, by the way, when I do this substitution and I move over to this substitution, if you're like, oh, I don't know those identities, don't worry about it. Again, this is another one of those ones where if you can't match your answer on the AP exam, if this was multiple choice, then you just move on, make your best guess, and move on, because the next substitution will be even harder for you. 1 over cotangent squared y is basically the same thing as the tangent of y. So this is negative tangent squared y as my final answer. So those are their cute substitution tricks. And by the way, if you want to familiarize yourself with those identities, these identities, I will write them down for you, that cotangent squared y is equal to cosecant squared y minus 1. And the other identity that I'm using is the reciprocal identity. So you should know that tangent of y would be the same thing as 1 over cotangent of y. And maybe what you did not know is that if I square both sides, that is allowed. So I am allowed to do that, okay?